Welcome back, and a big round of applause to Xavier and Antonia for Giant Swarm. They are gonna do live demos, so fingers crossed everything will go smoothly, but I'm pretty sure. Good luck then.
Thanks a lot. Hello. My name is Antonia, and this is my friend Xavier, and we want to talk to you about Kubernetes at the edge today. We're also going to show it to you in action, so let's hope that the demo does not fail. We want to start with a little intro to edge computing first, for those who may be unfamiliar with it at this point, what it is, how it's used in the industry today, and then we want to dive into a specific project, which is called KubeEdge. We're going to look at the architecture and then we're going to do the demo. So at the end of the demo, we want to anchor it a little bit into the real world, how it compares to an actual industrial setup, and then hopefully we can have a discussion at the end. So edge computing, what is that? According to Gartner's glossary, edge computing is part of a distributed computing topology where information processing is located close to the edge, where things and people produce or consume that information. Now, how does that look like in practice? If you look at the slide, you can see a factory at the bottom of the slide, and then you will also see a couple of clouds. So a factory can be such a place where information is produced, among other things, or rather more than information, it is some sort of data. And this data usually comes from such machinery as sensors or actuators, some machinery, and we refer to these kinds of machines as IIoT devices. So an IIoT device is an industrial Internet of Things device. Now, traditionally, we will send all of this data from these devices up to the cloud for processing. However, this may be slow, or it can be quite expensive to do, and also sometimes it's just not possible to do this at all. And this is where we introduce this additional layer between the device and the cloud, which we refer to as the edge. As you can see here in the screen edge section, there are a couple machines. And you can think about these machines or servers as being physically close to the devices, so being in the same network. Now, why would you want to do this? There are a couple of reasons. Here's 4. The first one would be latency. If, for example, your edge device is a self-driving car, you're not going to want to have any latency, right? So you want to make really quick decisions. Then also bandwidth can be an issue. So if you have a lot of raw data that is being produced by your machinery or whatever you may have, you cannot actually stream everything to the cloud, and it will be useful for you to do some sort of pre-processing before doing that. Autonomy is another big one. So in case of factories, as an example, if your factory is in a remote location somewhere in the mountains or something like that, your network is often not that reliable. So it might be down a lot of the time, and you still, of course, want everything to function properly, right? Then there's privacy. There are lots of regulations that might stop you from putting all of your data into the cloud, or you might just not want to do it, maybe for user trust issues or some other reason where you would rather keep this data close to your premises. Now, there's a few fields where we already use edge computing a lot. Here's a couple: IIoT, retail, smart cities, telco, healthcare, space. This is not an exhaustive list, of course, so new use cases are being added all the time. But what we're interested in right now is where Kubernetes comes in here, and I think Xavier is going to tell you about that a little bit.
Okay, so we've talked about edge computing, and now we're going to look at why we would need Kubernetes over there. So there are a number of challenges when working with edge computing, and as we saw, there are a few, but the main 3 ones are scale, connectivity, and updates. So when running workloads at the edge is much different than running them in a data center or in the cloud. So first off, you might have to scale to thousands of small nodes and devices across many locations, which is really like quite common. Secondly, these locations might be resource constrained. They might have bad connectivity, so those devices might remain offline for a period of time. And third, despite of that, we still need to ensure that those devices are updated and patched consistently, just like any other Kubernetes cluster in the world. And this is where Kubernetes already solves most of these challenges for traditional IT by being declarative. So having a declarative API means that we describe a desired state and then the system will make it real for us. It is portable, so we can run the same applications whether we're in the cloud or at the edge in our case. We use reconciliation loops in controllers, so the traditional Kubernetes way of life. So we save some manual operations and we get the use of the familiar Kubernetes API that we already use at work every day. However, vanilla Kubernetes works on the assumption that stable networking is a fact, where like usually in the cloud and data center, but this often breaks at the edge. And this is where KubeEdge comes into play. So this project was started in 2018 by Huawei in China, with the stated mission to extend Kubernetes to edge nodes and IoT devices. So the main features are to leverage the standard Kubernetes API at the edge, handle unreliable connectivity, and finally manage devices through the use of the device twin, digital twin framework, which we will talk about in a bit. So it entered CNCF as a sandbox project in early 2019, followed by a V1 a few months later. Late 2020, it went incubating, and last year, in October of 2024, it went into graduated, finally. So it's already adopted by the community quite extensively. And a couple examples that I'm going to talk about here. The first big success story was in China, where they overhauled the electronic highway toll collection system across 85% of the country. So originally, there would be like toll plazas, where you would get a human that collects the fare from the drivers. And these were replaced by overhead gantries with cameras looking down at the cars, with license plate recognition, so all automated. And this system would run on over 100,000 edge nodes, running 500,000 edge applications. And just to put this into perspective, this generates around 300 million data points every day. And it is said to have improved traffic efficiency 10 times. So quite a big success story here. And the next one, which is pretty cool, is about space. So the first cloud-native edge computing satellite, which is basically KubeEdge on your satellite. So originally, this application was for flood prevention and disaster mitigation. So you would have a satellite image an area. It would store the picture on local disk and then transmit it downstream to the ground station. Then the report would be compiled by a person. And this was kind of manual and time sensitive. However, in mountainous regions, you might have like cloud covers, bad weather, meaning the photograph would be taken, transmitted, but it would be useless because you couldn't see the actual region. So in 2021, China launched the first satellite connected via KubeEdge. And what it does is it embeds a small AI model on board. So when the picture is taken, this AI model will identify the cloud cover and analyze like the water levels, do all this pre-processing stuff, and determine whether the image is worth transmitting. If it is, the data is processed by a more powerful AI model on the ground station. It is all automated and is said to have reduced disaster response time from days to hours, which is quite impressive, and data transmission by around 90%. Now, these are just two use cases. You can find more on the public website, kubeedge.io/case studies. There are quite a few, but these two ones were the most interesting ones. And now we're going to take a look at some architecture.
Nice. So this is the fun part where I'm going to show you a couple of diagrams with boxes and arrows. So before I go into any sort of detail, I want to give a bit of an overview about what KubeEdge looks like on a Kubernetes cluster. So you will recognize this cloud edge device trifecta here from the previous slide. And when you look at the cloud layer, you have to be aware that this is not necessarily a cloud provider in this case. This can be any Kubernetes cluster, so your cluster can also be on premises, and oftentimes it is. So on the cloud layer, the first thing you will notice is the cloud core, and this is actually the only entry point from the Kubernetes API into the edge. So all of the communication between your Kubernetes cluster and the edge will go through the cloud core. On the edge layer, you have the edge core, and one edge core is installed on every edge machine. So you see one here, but there can be thousands of them, as we just heard. And again, those could be satellites or toll stations or something else. The edge nodes join the Kubernetes cluster by connecting to the cloud core, and they will look like normal Kubernetes nodes. So they have a special label on them, which you can use to schedule your workloads at the edge. But other than that, they look pretty regular. The edge core is installed as a single binary on the machine. The edge core talks to the device layer via MQTT protocol, and it also talks to local applications via HTTP. And on the device layer, you can find your actual devices. So again, sensors, robots, cameras, and so on. And KubeEdge also offers a framework where you can represent these kinds of machines as Kubernetes custom resources, which we will talk a little bit about later. I have marked here the Kubernetes API related streams in blue and the ones that are related to the devices in red. So maybe this can make the following slides a little bit easier to follow. First of all, let's look at the cloud core in a bit more detail. The cloud core is installed as a Helm chart in the Kubernetes cluster. There is an upstream CLI tool that you can use to do this, among other things, and it's called KeyADM. And it has a couple of components. So the first component you see here is the Cloud Hub, which is a messaging broker, and it keeps open a secure, persistent channel to each of the edge cores, and it does so via WebSocket or even Quick. The red and blue controllers here are doing a couple of things. So the first one, the one in blue, is the edge controller, which propagates changes to workloads that run at the edge from the Kubernetes API to the edge. And then in the opposite direction, it also reports back things like statuses and events and so on from the edge to the Kubernetes API. Now the device controller, which is the red one, reconciles the device CRs, so the Kubernetes custom resources that I've mentioned earlier, and it syncs between Kubernetes custom resource and managed devices. Now bundling all of the communication like this through the cloud core has a couple of benefits. So the first benefit that you get is load reduction, and this is done through aggregation of updates. So this means that instead of basically sending updates from all of these edge nodes to the Kubernetes API server, you aggregate them, and so you don't overload the Kubernetes API server that much. And then you also get resilience across flaky networks via incremental updates. And this means that in case some of your nodes disconnect and then they reconnect after some time, you don't get all of this built up updates all at the same time, but this is done incrementally. This way you can actually integrate the edge into an existing Kubernetes cluster, and it has been shown that up to 100,000 nodes could be added to your cluster, basically. Let's also take a look at the edge core now. The edge core has a memory footprint of around 70 megabytes. The edge core also has an edge hub, which is the counterpart to the cloud hub on the edge, and again, it connects through WebSocket or Quick, and it has the job of routing all the messages from the cloud to the correct edge modules. It reports back node and device status. It also takes care of things such as keep alive and routing messages to the correct modules within the edge. There are two important modules that you can see here that both work with local state, the meta manager and the device twin. So the meta manager is a cache and message processor, and it stores data like the pod state and config map contents in a lightweight database. This is like an SQLite database, and this is so that when your node disconnects, it's still functional and has all the data it needs. And then it will sync later on when the connection is back. The device twin keeps track of the state of devices, and it manages attributes and status of devices. This will sync information to applications that run locally at the edge, but it also will sync that information to the cloud. Now you can see the little guy here on the lower left that is called HD, and you have to think about HD as being the kubelet of the edge core. So this will talk to the container runtime so that you can run workloads on the edge just as you would in the cloud. All the communication at the edge will go through this common messaging system here that is called Beehive. This is unique to KubeEdge. On top of all this, you get two buses. The first one is the event bus, and this integrates with the MQTT broker. And then it connects edge modules and device mappers. And device mappers in turn connect to actual devices via device protocols, but we will get to this a little bit later. Now the service bus provides HTTP communication with local apps and APIs. And you can also see the container runtime here, which is in charge of the lifecycle of pods, as you've heard. And you can see at the bottom there is the mapper, which translates between MQTT and some device-specific protocols. All of this taken together, all of these components will allow edge nodes to keep running workloads and manage devices, even when the connection to the cloud is unreliable. Let's talk about devices.
All right, so now we have an edge node which is joined to our Kubernetes cluster. This is, by the way, already a very good use case for KubeEdge because that lets you schedule workloads on your edge devices. However, we can go a bit further with the device capabilities of the project. And this is where we get into the IoT territory indeed. So over here, it's all about protocols, you know. All these logos, you can see down there. Communication protocols, they are used to standardize and how data is collected, transmitted, and exposed for our consumers. So an IoT device is just a thing that generates data. So think sensors like cameras, temperature, pressure, these kind of things. And these will be exposed on several protocols like Modbus, on VIF, GI, GE, or there are a number of them. But you could think of an IKEA temperature sensor that connects to your Home Assistant instance via Zigbee, for instance. It is kind of the same thing, except here we want that data sent into KubeEdge and consumed by a professional, like industrial grade system. And this is where the mappers come into play. So mappers are translators between the physical world of our devices and the KubeEdge logical world. So in the industry, we often refer to them as adapters, like HiveMQ-Edge, for instance, that's what they call them. KubeEdge refer to them as mappers because they map a protocol to something that KubeEdge understands. And here we can see a visual representation of these. So on the right-hand side, we have the hardware devices that generate that data. And on the left-hand side, we have KubeEdge, where our edge core and stuff live. In the middle, we have these mappers, so one for each protocol. So these mappers are just containers running on the edge devices. They know how to talk to the hardware devices, they collect the data, and they transmit it to to KubeEdge via the messaging service. So there are already a few mappers available upstream for you to consume. But if you want to build your own because the protocol you want to use is not available, you can build your own. There's a framework written in Go. And there's some documentation for you to use. And once we have our mapper, we need to describe those hardware devices as resources in Kubernetes. So there are several custom resource definitions when you install the KubeEdge Helm chart. However, the two we are going to focus on are the device model and the device instance. So the model is just the properties that describe a specific type of devices, whereas the instance is the actual device you will deploy at a specific geographical location. So IKEA is great, but in the industry you would have something more like that looks more like this. So this is an Advantech Adam 6017. I have never touched or seen one of these myself. I just Googled something on the internet that was simple enough for this demo, or for this example. So it has 8 channels to which you would connect sensors, and each channel has register, like Modbus registers mapped to them. Compatible Modbus, Ethernet. And when you create this into KubeEdge, this is what it looks like on the left-hand side. So you have a device model kind resource. And we have a property for each of these 8 channels. So you can only see 0 and 1 here, but you would have 0 to 7 in the real world. And finally, we have the protocol which is set to Modbus, for which you would need like a mapper that is registered against the edge core as Modbus. And on the right-hand side, we have an extract from the user guide for this specific device, the Advantech 6017, where you can find the register address for all these Modbus channels. And we're going to need to use these in the device instance CR. So each of these properties are mapped to an address. This will tell our mapper how to access which sensor, for instance. And on the left-hand side, we have a device model ref, kind of like when you have like owner ref in your other Kubernetes resources, same idea, and config data on how to access the device on Ethernet with an IP and a port. But I think you came here for a demo. Hopefully it will work. Let's see what happens. So this demo is kind of a simple use of the KubeEdge stack. We use a Raspberry Pi and a USB webcam, consumer grade. And this is what the webcam sees. We're not going to see that here because we run this thing in a container, but you can run this app on your own laptop, and this is what you will see when you raise your hand in front of your camera. So the way it works is that webcam is connected to the Raspberry Pi. The Raspberry Pi runs Raspberry OS with Edge Core, and it's connected to a CAN cluster running on my laptop. Now, this application that generates this image is a Python app that we wrote with Google Media Pipe Framework, which uses OpenCV. It lets you do like hand gesture recognition, facial recognition, but we use the person posture, so it creates like data points for each of your joints, for instance. And in our case, we extrapolate a shoulder line, and any hand detected above this shoulder line is considered as raised. You can see up there, like I have my 2 raised hands. So this is what happens behind the scenes. Now, taking this into account, as you can see, there is 1 shoulder line. So this demo kind of doesn't really scale to like an audience like that because I see many shoulders here. But we're going to work with the front row if they don't mind too much. We're going to double check that it works ourselves, though. So let's take a quick look at that. So it's going to be tricky with the mic, actually.
Should I hold your mic?
Yeah.
Okay, I'm going to be your mic stand.
Okay, that's good. Okay, so I'm going to install the mapper. It's kind of distracting. I'll figure. So I'm going to show you what it looks like first. So here we have, I'm going to zoom in a little bit. Oh, wrong. I'm going to zoom in a little bit. So you can see that we have our CAN control plane node, and we have the Raspberry Pi KubeEdge node. So same thing, except we have a suffix to the version, and we have an extra label to give it like a role of agent. So if I describe that node, you will see that it's exactly the same as any other Kubernetes node that you could get, like, except here we have like this extra label. We have the Cloud Core IP, to which we've joined with the join token, and then you get the same things like resource request limits. We have an ARM architecture because it's a Raspberry Pi. So all of that is very similar. You can see that we have some pods. So it's kind of cropped here, but we have some pods running on the Raspberry Pi. You can see on the right-hand side, some of them are already running on the Pi. So now we are going to install the device mapper first. Yeah. I'm using my history, so I can use only 1 hand. Okay, so we can see that our mapper, here's MQTT mapper is running. If I look at its logs, it has started correctly. So now I'm going to install the CRDs, so the device model and the device instance. So we install the model first because the instance has a ref to the model. And it is there. And now if we look at the device, so we're not going to look at the model, it's not that interesting. But the device here, you can see that it's called, we call it hands because we're talking about hands here. We have a protocol config data on how to access the MQTT broker. We have an initial value of 0 raised hands, and this is our twins. We talked about device twins, digital twins. This is what we're talking about here, a representation of a device in the Kubernetes world. And now I'm going to install that Python app with media pipe. It's somewhere around there. All right. And from there, we are going to visualize the data with a Grafana dashboard. And I just remembered that I need to port forward my Grafana. All right. So now we have a value of 0. And if I use my assistant to raise her hands, hopefully, I'm trying not to shake too much. Maybe we'll get a value to change. Yes, if you have a second hand, maybe, just to show.
Sure.
Okay, so we have this media pipe that sees the hands raised. And when you take them down, then the value goes down to 0. So I'd like to, like we've tried this before, it didn't work that well with the audience. I'd like to try again. So we're gonna kind of have a quick look. Do you mind, front row? Let's see, because sometimes with the distance, it kind of, we have.
Yeah, it seems to be working a little bit this time.
It's kind of finicky with like resolution and distance. Okay, we have a value of 2. So who's got pets here? So when you raise your hand, you need to keep it up like for a few seconds because there's like latency. We have a smoothing function to avoid flapping. Okay, we have 1 pet. Who is running Kubernetes in production? Right. I think we need a better camera for this. But you get the idea. So, yeah. Now, if we want to, I think you guys like black screens and terminals. So let's take a look at the terminal again. So here we're going to take a look at what it looks like. So in the top left corner, we have the device twin in the Kubernetes resources. Top right, we have the MQTT mapper. We just subscribe to the same topic the app is publishing to. At the bottom, we have the logs of the mapper. So I'm just going to zoom in a little bit. So you will see like a difference in latency between when device twin is updated and the actual data is published by the app. So it will change to red when the data change on the device twin. Can I try again? So as you can see, like the right-hand side was much faster. It's because there is this processing between the mapper going to the edge and the edge updating the Kubernetes API. And at the bottom, we can see that the logs are processing the number of hands detected and the number of raised hands. So this app is somewhat limited because we've done our best to make something that works. But you kind of get the idea of what we are trying to show here. And now we'd like to talk a little bit about the setup, show you how it's installed, how it works. And here you see the same 3-layer diagram that we talked about a couple of times earlier. So at the top, we have the cloud layer, which is our CAN cluster running on the laptop here. This is where Cloud Core lives and our observability stack. In the middle, in the edge layer, we have the Raspberry Pi with the edge core, the mapper, and the MQTT broker, which is embedded with KubeEdge. And at the bottom, we have the device, which in our case would be the combination of the Python app and the USB camera. So if we want to talk a little bit about the mapper itself, the way it works actually, so the Python app is configured to publish a message onto a specific MQTT topic on the broker when it detects a raised hand. And the mapper is going to subscribe and watch this topic. So when it picks up a change of data, like a new message, it will update the device twin in KubeEdge, and it will expose that value on a metrics endpoint, which is created by our Prometheus instance and exposed by Grafana. So we have some tweaking to get like 1 second intervals. Kind of dirty, but whatever. So this is where the edge side processing would happen, like satellites, gantries, that would be in the mapper. And if you want to take a look at this whole thing, the setup, so the MQTT mapper, the Python app with MediaPipe and CRDs with the devices, the device and device model, you can scan this QR code. So it's our public repo. You will find everything there. I'll give you a couple seconds to scan that. And 3, 2, 1, go.
Oh yeah. So this is a very simple demo, and it does not really look like something someone would do in their factory. However, let's compare side by side and see how this might translate into an industrial grade setup. So instead of counting hands, for example, we do have a customer at Giant Swarm who detects holes in paper production. In this case, instead of a little USB webcam, probably they would use something more like remote cameras, which are accessed by protocols like ONVIF or sensors. Then we have the Pi and the Python app, and you might find comparable, although probably more well thought out AI models for analytics in production lines. And these would process the feed from the camera running on the edge node, kind of in a similar way as what we just did, right? So our mapper, as we've heard, is based on MQTT, so it does not translate anything. It just uses MQTT as an in and an out. MQTT is actually very commonly used in industrial IoT setups. However, more commonly you would also see this combined with some sort of translation mechanism, as we've talked about, from another industrial protocol to MQTT. Also, industrial mappers or adapters may include some sort of pre-processing, more business logic than what we've been doing. The device twin with the CR representation in KubeEdge in the demo is comparable to the use of digital twins in the industry. Then the one big difference, in my opinion, would be the Prometheus use. You probably also thought that using Prometheus in this way is not very ideal, so we do not recommend doing this at home. However, still you might find some data collection which is going to produce time series data, and then this time series data is going to be used in some database and processed further in some IoT solution that the factory or another application might use. So again, this may be a simple demo and it may be a little silly, but it does contain a representation of real-life industrial solution with all of the layers. So the whole point of using edge computing would be to keep critical processing at the edge for low latency and resilience while syncing the data to the cloud for further processing. And I think it did show that. So with all of that said, thanks a lot for listening to this, and thank you for raising your little hands. It was very beautiful. You made us very happy. And now, if you have any questions, please speak up.
Yeah, I'm running with the mic.
Thank you very much. I really enjoyed the talk. As I understand correctly, the edge nodes are first-class citizens in your Kubernetes cluster, and the role is just different. And I'm wondering, some cloud providers prevent you when you're using managed clusters on their cloud. They do prevent you from adding your own nodes outside of their own infrastructure. So, well, that's an incentive to rent their infrastructure for virtual machines, and adding some edge nodes in that case might be prohibitive or difficult, right? Because you wouldn't be able to connect additional nodes outside of the cloud provider's infrastructure to your cluster, to the managed cluster. Is there a mode of operation for KubeEdge that would allow you to operate this component in such an environment? Like, let's assume you have a chicken farm. I talked to a friend actually, and he told me like a chicken farm can actually generate upwards of 15 gigabytes of data, IoT data, per minute. And it's just, it's kind of funny, but it's a real use case. And you can't really expect AWS or like Akamai, GCP to have a node on site to your chicken farm, right? But at the same time, you need the node to be a first-class citizen in your cluster. So that's my question to you.
So at Giant Swarm, we have our own bootstrapping cluster, and we own the nodes. Like we use kubeadm. Like now, if you want to go and use EKS or AKS, I would suspect that if you have the right permissions, it might be able to join the node, because you have this kind of intermediate layer of running your cloud core, which is kind of the translator between your K8s API and your edge node. However, we haven't tested it, so I couldn't tell you for sure whether this would be technically possible. But yeah, I would be surprised if it wasn't an option at all. But because it's not managed, maybe not. I would have to check that.
Yeah, I will be interested to actually test this. I'm actually working on the Akamai Kubernetes offering, and this is a typical use case where some customers do want to connect their own nodes on-prem to the managed cluster. It has some implications in regard to revenue, but this seems like a very legitimate use case for having your own nodes outside of the cloud.
For sure, yeah.
So thank you very much. That's all from my side.
Thank you for that question.
Thank you.
Any more questions?
Thank you for presentation. You said that a single Kubernetes cluster can have up to 100,000 of these edge nodes. And as I know, Kubernetes, traditional regular Kubernetes cluster has a limitation on the number of nodes in something like 60,000 of nodes or something like this. And you said that you have installations with 100,000 of nodes, and my question is, how did you achieve this, and is it hard? What is the limit on the number of such edge nodes in a single Kubernetes cluster?
So this 100,000 node case, I took this number from a benchmark that was published by KubeEdge. So I have personally not gone and added 100,000 Raspberry Pis to my Kubernetes cluster. However, you can find this if you go to the KubeEdge project. They have like a pretty detailed setup of what they've done exactly and the results. Like there are some graphs, so it's pretty interesting to read that. What I'm not sure about right now is if there is an actually in production use case, like one of the ones that use KubeEdge with that high number.
I think that would be the one with, it was in partnership between Huawei and the Chinese government when they did this first, like the first use case I showed. But honestly, I think having 100,000 device like Kubernetes nodes in the same cluster might not be the most optimized way to do things. I don't work for Huawei or for that use case in particular. But this is basically how they claim that you can do 100,000 nodes, because they've done it with that use case. Yeah.
And another question is, in Kubernetes, in regular Kubernetes, pods are started on some nodes, and if this node become unavailable, become offline, then Kubernetes reschedules these pods to other nodes. And how this scheme works in these edge nodes when connection disappears from these edge nodes?
So if the connection disappears, it's not going to reschedule the node on another, the pod on another node. So the Edge core has like this embedded database on how to, like, what pods to run, like the desired state of things. So the node becomes like autonomous. And when connection is re-established, then there will be a synchronization between the Edge core and the Cloud core via these hub components. But this is kind of the point of this thing compared to a K3s, where it would be like a regular Kubernetes node where you would get this the 5-minute like eviction delay. In this case, the pods won't be rescheduled. So this is kind of how you avoid split brain scenarios.
Any more questions? If not, then big applause.
Thank you.